Hi, welcome to this presentation. In this example, we will take text classification as a demo, and we will learn how to configure the random embeddings for the text tokens, and we will also see how to train the random embeddings in the classification model. For this example, I'm taking a bunch of sentences, and these sentences are tokenized. Here on the right hand side, you see all the tokens or the words, and the words are typically sorted and assigned token ID starting with 0, 1, 2, 3, 4. And from the tokens, I'm creating a few sentences, 1, 2, 3, 4, 5 sentences for this example. And each sentence will have some tokens or certain number of tokens just to pretend that we have sentences. Then sentences with the token IDs, and we're going to use them to train um, a deep learning model in Keras. For example, sentence one, and this is a token. Sentence two, three, four, and five. And as I mentioned earlier, for each token, we will have token IDs also. So a particular sentence, for example, dog runs, eats, will be represented using the token IDs 11, 1, 4, so now for all the tokens that I have in this particular corpus or the demo, I will also have random embeddings assigned. So if you see the column number 3, which is the embedding 4 dimension, for this demo, I'm using hypothetical 4 dimension random embedding. Initially, all the tokens will be assigned random embeddings. For example, here, sentence 1, token ID 0, 15, 2. For each of the token, for example, token 0, and this is the random embedding of 4. Token number 2, this is the random embedding of 2. And likewise, we have the random embeddings generated by either you can use a NumPy or Keras or any other package to generate the random numbers for the embedding. Now, for every sentence, we have to average the token IDs. Essentially, for these token IDs, we have individual random embeddings, and we are going to average those three to get the averaged embedding. So essentially, now the averaged embedding is representing my sentence. Moving forward, I'll show you how to use these average embeddings in a deep learning model. So for example, now this is the outcome of the averaging step in our model. For every sentence, we have the averaged representation of the sentence. Now comes the deep learning models. We start with the first sample, and we use that first sample to train a deep learning model. For example, this is the sentence, and the particular sentence with the average embedding. This is the average embedding, like I showed you in the previous slide. So since there are 4 numbers in the embedding, I will have 4 input columns in the model. And for example, here in this demo, I have hidden layer comprising of 4 nodes, but it can be any number of node as per your design. In this case, we have a dense network. All the input neurons are now connected to every neuron in the hidden layer. And after that, we have the output layer connected with the hidden layer, and that gives us the output. So in this particular demo, we have a text classification problem. So that means we will classify the text in terms of positive, negative, or some kind of a sentiment like, positive or negative or 0 or 1. So this is how my data looks like. One sample we will send to the model, and the model will receive it. Essentially, it will receive 0.1, 0.1, and zero point 0.3 and 0.09 as the input, and then it will produce an output. That output will be compared with the actual. That gives you the loss function, and we use the loss function to compute the gradient, like in any gradient descent model. And using the gradients, we're going to update the weights at this layer, and also the weights at the hidden layer, hidden and input layer. What is interesting now is In this case of embedding or random embedding, the Keras model also needs to update the embedding which we initialize randomly in the first step. So these particular embedding for the token 0, 15, and 2, 0, 15, and 2, particularly those three token embeddings will also be adjusted as per the loss function. And this process is going to continue for the next sample, exactly the same thing. And you are providing the input to the model. Model computes the loss, and using the loss and the gradient is going to update the relevant token representation. In fact, the embedding for those token, for example, 1114, you notice 1114, those are the tokens being adjusted as part of the back propagation. Likewise, this process will continue for the other sample in the batch. And in the end, you have the deep learning model trained. Essentially, what we did so far is batches of input going through the forward propagation, loss calculation, and the backward and the update rule, which is going to update the parameters. So updating the weights and as well as updating the random embedding. This process is repeated over many iterations, and after that, what you get as output is embedding matrix along with the model weights. Now, when we so essentially we have the trained random embeddings here for each of the token as part of the training process or at the end of the training process. Essentially, what we did is loading the data set. So we have, for example, any text data set, for example, IMDb data set, which comes with, encoding representation or encoded representation already. You can use that. And after that, you follow the typical deep learning Keras modeling, pad all the sequences to a certain length. And the next step is to build the model. And here you're going to create the embedding layer in Keras, and each of the embedding layer, or rather the embedding for the tokens will be generated initially randomly, and then we're going to average those embeddings for the tokens in the input sample. And after that, we pass it to the hidden layer. And next, after the training, we need to save the model. The only difference here is as part of saving the model, you not only save the architecture, you also save the embedding matrix along with the weights and parameters. That's the additional part here. Once you save it, along with the saving the model, you should also save the tokenizer that you use to split the data or input data. The same tokenizer needs to be used for prediction as well. So this also needs to be saved as part of your artifact. Next step, so saving the training configuration, that might be also essential. For example, what is the vocabulary size? What's the embedding dimension? What is the max length of padding? And so on and so forth. So these parameters also need to be saved along with the previous two that I mentioned. After saving, you need to load the model and do the prediction. So loading the model, so means the weights, and loading the tokenizer, and also the configuration parameters. Processing the new input. So if you have a new input, for example, this movie was amazing. So tokenizer will split it, and it will generate the token ID. And for the token ID, is going to get the relevant embedding from the embedding matrix. For example, here, movie was fantastic, and this is going to be broken into tokens. For example, these are the tokens. Also, padding is required. So, for example, we are going to use a max length, and we have the padding done here, so that now your rate data is ready for prediction. So now, next step is to after the padding, we look up the token IDs from the embedding matrix, and we retrieve the embeddings, which are basically trained embeddings from the previous step of training. And after that, we get the averaged embedding for all the tokens. So that's part of the global average pooling step. Here, you're going to get the output as one single 4-dimension vector, for example. So this is now representing your input sentence that you are trying to predict. That goes through the dense layer, exactly the same configuration as the training. And that returns you the output. Output could be 0 or 1, depending on the prediction probability. That's pretty much how you save the model using random embeddings and use the model for predictions. Now we'll try to understand the reason why MLP based architecture, which we used previously, may not be sufficient for sophisticated sentiment analysis. Although it may work for certain use cases, but for advanced level, it's not going to work. It's going to ignore your word order. All the words are treated equally in the MLP. There is no differentiation. So we need to use a different architecture called recurrent neural network. Couple of examples. The movie was not good. Okay, so here the word good has a strong positive sentiment. So if you use an MLP model, most likely going to get the prediction as positive. But when we learn about RNN, we'll see how RNN differentiates the output here in this case because it's going to use the word not along with good together. So that's missing in the MLP. Similarly, the plot was bad, but the acting was great. Again, notice here the presence of the word but. These things are not handled by typical standard neural network, and that's where RNNs actually shine. So next, we'll try to understand essentially the RNN cell's internal mechanics, how it would input the data and process it, and then we will also learn about the overall RNN architecture. Thank you all.